is a brief tutorial on balancing chemical reactions. A chemical equation is a symbolic representation of a chemical reaction that shows the reactants on the left-hand side of the equation and the reactants what you begin with. Products are on the right-hand side of the equation, and they are what's produced in the chemical reaction. The relative amounts of each reactant and product are shown using stoichiometric coefficients. These give the number of each and the proportion in which each reactant or product are in the reaction. These are some symbols that are used in chemical reaction. The plus sign is read plus or added to, and they're written between individual reactants and products. The arrow is read yields or reacts to form or something similar. It points from reactants towards products. Then we got the S, the L, the G, and the AQ in parentheses, and those refer to the solid state, the liquid state, the gas state, or aqueous solution, which means it's dissolved in water. The triangle is occasionally written above the arrow, which means you have to add heat to make that reaction occur. Chemical equations are an attempt to show in a written format what's going on at the atomic and molecular level. If we take this reaction for instance, we've got methane reacting with 2 oxygens to produce CO2 and 2 waters. Notice we added coefficients to the O2 and the H2O to balance out each element in the equation. Looking at it, the gray sphere represents carbon, the white sphere represents hydrogen, the red sphere represents oxygen. We can see that we have 1 carbon on each side of the equation, we got 4 hydrogens on each side of the equation, and we got 4 oxygens on each side of the equation, indicating a balanced chemical reaction. Law of conservation of matter states there's no detectable change in the quantity of matter in an ordinary chemical reaction. The balanced chemical reaction must include the same number of each kind of atom on both sides of the equation to be balanced. If we look at ferric oxide reacting with 3 carbon monoxides, where you add some heat and produce 2 irons and 3 carbon dioxides, notice we've balanced the amount of each type again with stoichiometric coefficients. What does that mean? It means on the left-hand side we've got reactants, on the right-hand side we've got products. So that means that we got 1 formula unit of ferric oxide reacting with 3 molecules of carbon monoxide to form 2 iron atoms and 3 carbon dioxide molecules. And it's okay to look at it on this small scale, but how often do I have 1 formula unit and 3 molecules reacting? Generally we'll have much larger amounts than that, so it makes sense to relate them using moles. So we can say 1 mole of ferric oxide reacts with 3 moles of carbon monoxide to form 2 moles of iron and 3 moles of carbon dioxide. Turns out that's a much more useful relationship. If we do it in mass, we find we got 159.7 grams of ferric oxide reacting with 84 grams of CO2, because that 84 grams represents 3 moles of carbon monoxide. And then we got 111.7 grams of iron representing 2 moles of iron, and 132 grams of CO2 representing 3 moles of CO2. If we add the masses of the reactants and compare that to the masses of the products, we find within a reasonable rounding error we've got the same mass on both sides of the reaction, meaning matter has been conserved. Let's look at an example here. Look at the combustion of propane, C3H8, where the C3H8 reacts with O2 to form carbon dioxide and water. Here below we've got a table where we can put the numbers of each type of element to keep track of the balancing. So let's look at how it begins. On the reactant side we've got 3 carbon atoms, 8 hydrogen atoms, 2 oxygen atoms. Now on the product side we've got 1 carbon atom, 2 hydrogen atoms, 3 oxygen atoms. It'll work out better if you save the O2 for last, because I can add a coefficient to that without changing anything else. So let's add a 3 coefficient in front of the CO2 to balance the carbon. but they'll change the carbon and the oxygen, so that means I've got, on the product side, 3 carbon atoms and 7 oxygen atoms now. Now we can balance the hydrogen by adding a 4 in front of water. That'll balance out the hydrogen, but it'll also change the oxygen on the product side. So that means we got now 8 hydrogen atoms and 10 oxygen atoms on the product side. So the carbon and the hydrogen are balanced, so I need to add a coefficient to that oxygen that will balance out the oxygen on the product side. If I stick a 5 there, that will give me 10 oxygens on the reactant side, having 3 carbons, 8 hydrogens, 10 oxygens on both sides of the reaction, indicating the reaction is balanced. Let's look at this next reaction, where we got ammonia reacting with oxygen to form nitrogen monoxide and water. Again, let's look at how we start. We got 1 nitrogen, 3 hydrogens, 2 oxygens on the reactant side, and we got 1 nitrogen, 2 hydrogens, and 2 oxygens on the product side. Only thing that's not balanced initially is the hydrogen. So we got 3 and 2, so we'll find the least common denominator of 6. And so 2 times 3 is 6, 3 times 2 is 6, so I'll put a 2 coefficient in front of the ammonia, a 3 coefficient in front of the water, and that will give me 6 hydrogens on each side of the reaction. But it also gives me 2 nitrogens on the reactant side now, and gives me 4 oxygens on the product side. So I've unbalanced that nitrogen, so let's stick a 2 coefficient in front of the NO. That will give me 2 nitrogens, but it'll also change my oxygen number to 5. So now the nitrogen and the hydrogen are balanced, the oxygen is not. But I cannot add a whole number coefficient to oxygen that's going to balance that reaction as is. But we could stick in a fraction, like 5/2, or 2.5. 2.5 oxygen molecules gives me 5 oxygen atoms. However, that balances it, but we don't like having fractions in our final answer. At this point, we have 2 nitrogens, 6 hydrogens, 5 oxygens on both sides of the reaction. It's balanced, but again, we don't want that fraction. What we want to do is multiply through by the denominator of that fraction, and that will give us a still balanced reaction, but we'll get rid of the fraction. So we change the coefficients and double them all and say 4 ammonias, 5 oxygens, 4 nitrogen monoxides, and 6 waters, and then we double all the amounts of each. So we got 4 nitrogens, 12 hydrogens, 10 oxygens on both sides. So we've gotten rid of the fraction, the reaction's still balanced, and so we can say we're done. Let's look at this last reaction that we'll consider. Aluminum sulfate plus barium chloride forming aluminum chloride and barium sulfate. For the purposes of this reaction, we'll consider sulfate as a unit instead of individual sulfur and oxygen atoms, and in many cases, if you can see the polyatomic ion has not chemically reacted in any way, you'll find that it's easier to just consider the polyatomic ion as a unit, because it's easier in trying to balance all those oxygen atoms if you got more than one oxygen containing polyatomic or something like that going on. Let's consider where we are initially. We got 2 aluminums, 3 sulfates, 1 barium, and 2 chlorines. On the product side, we got 1 aluminum, 1 sulfate, 1 barium, and 3 chlorines. Let's balance the aluminum first. We'll stick a 2 in front of that aluminum. That'll alter the aluminum and the chlorine. So now we've balanced the aluminum at 2, but that gives us 6 chlorines on the product side. Now we can balance that chlorine by adding a 3 in front of the barium chloride, but we need to balance that barium now, so we'll add a 3 also in front of the barium sulfate, which turns out to balance the sulfate as well. So we see that we got 2 aluminums, 3 sulfates, 3 bariums, and 6 chlorines on both sides of the reaction, meaning that reaction is balanced. This has been a brief tutorial on balancing chemical reactions.